This is a talk about history. If you are relatively new to Kubernetes or Cloud Native, then there's going to be a ton for you to learn today. Regardless, unless your special interest is like the history of computing or you're like 95 years old, you're still going to walk out of here having learned something, because what eventually got us to Kubernetes is super old, it turns out. First of all, my name is Cosgrove. I'm a lead developer advocate at Dell. That is my cat, Espresso. She's 20 years old. Her birthday is next week. Please say happy birthday to my cat. You can find me on Twitter still, regrettably, at Dixie3Flatline, and my work email address is cat.cosgrove@dell.com, but I really wouldn't try emailing me. I'm not going to respond to that. I'll like mean to and then not do it. So, Kubernetes is actually just another solution to a 60-year-old problem. It is indispensable in situations where it's useful, but it is undeniably complex and often kind of difficult to use. In fairness, some of that is because of how new it is, right? We're still on version 1X. It was only publicly released in 2014. It has not been that long in the grand scheme of things. And eventually, more tools are going to be built on top of it that reduce this apparent complexity to something a little bit more manageable for most people, right? Or at least for people who haven't shifted their entire careers like we have to specialize in it. But this is not a unique problem to Kubernetes. It's not surprising that it's difficult. It's not special for being difficult. This happens all the time, actually. Same with the newness. CI/CD feels new-ish, but its origins predate DevOps. Infrastructure as code feels even newer, but we've been programmatically defining machines and application workspaces for decades. That's not new either. What's actually going on here is that we are solving the same technical problems over and over and over again, flavored by the circumstances of the time in which some pain point becomes impossible for us to ignore. Kubernetes is no different. Since the dawn of virtualization, we have had issues with workload and scale. So nearly every revolution in tooling, since we finally nailed the core concepts like virtualization, has been just an abstraction layer built on top of an abstraction layer, on top of another abstraction layer, solving for something that was previously very difficult to accomplish. And that's great, but it comes with a downside. And that downside is that the further we get from the origin of a piece of tooling, the less we remember about what was going on in technology at that time that made that change necessary. We forget the context of a situation, and then learning that tool decades on from the context in which it was born seems harder, because you don't remember what it was like to do without, right? So like Jenkins, for instance, Nightmare, seems difficult to use until you try managing deployments 3 times a day by hand. That sucks. That is super difficult. Terraform is confusing unless you've had to define and maintain infrastructure by hand for dozens of wildly different environments. Nobody wants to do that, and that's not too far in the past, really. And Kubernetes seems hard until you have to dynamically scale an application to hundreds of thousands of users without it. Virtualization seems like a lot of work until you try to accomplish that same task on only one machine that can only run one thing at a time. So a pretty common question when somebody is first kind of learning to use containers and first getting involved in Kubernetes is around the difference between a virtual machine and a container. This is a bit oversimplified, but it comes down to what is being virtualized. Virtualization is just the use of a computer to simulate one or more aspects of another computer, of the concept of a computer. And it's something we've been trying to achieve to varying degrees since very close to the dawn of computing. It's another one of those things that can feel new-ish, like VMs might make you think of like the 80s. It's so much older than that, and we've gotten quite good at it. The three types of virtualization you are probably most familiar with are hardware virtualization, so like a complete virtual machine, desktop virtualization, and containerization, which is just operating system level virtualization. But things like VPNs and distributed file systems are also types of virtualization. Kubernetes relies on a variety of types of virtualization to operate, and it so owes its existence to a very, very long history of a need to do more things faster, driving innovation. So this is an ENIAC machine, and this was the first real computer. In the very early days of computing, machines were physically enormous and extremely expensive. You generally did not own them. You were leased them by the manufacturer, by the company that owned them. This was never leased out. The ENIAC was owned by the Army. But obviously, you would want to get everything that you could out of this extremely expensive monolith that's taking up an entire room in your building. But they could only run one program at a time, right? You write your program offline using punch cards or paper tape a little bit later, and then you show up at the machine for your scheduled time to run your program, and then you stand there and wait for the output. They were basically just a big calculator back then. Eventually, we gained the ability to run multiple programs sequentially, and we called this batch processing, but you were still standing there just waiting for output. It's just that it could queue up another job after the last one. We had not yet figured out concurrency. But in 1959, the first patent was filed describing a system that would allow for multi-programming, and they coined the term time sharing for this, which now has very different connotations. Timeshares make you think of like a skeezy guy in Vegas trying to sell you an outrageously expensive vacation home. Different thing entirely. But MIT and Dartmouth and a bunch of other universities jumped on board immediately. But it turned out that the expense of the actual machines and the limitations of the hardware and the, at the time, complete lack of a general-purpose time-sharing operating system kind of meant that batch processing stayed the way we were doing things, even though time-sharing was sort of technically possible. But conceptually, this evolution from batch processing to time-sharing is the spark that eventually drove the adoption of virtualization and, after decades, got us Kubernetes. In order to ideally implement time sharing, they needed an advance in computing that at the time was still entirely theoretical. They needed to figure out how to virtualize memory. Today, this is so ubiquitous that you probably do not think of it at all. You don't notice it. It means that the user or an application is given the impression that it has access to a large and contiguous pool of memory, regardless of the actual reality of the hardware. And, oh, why did my slides go away? Time sharing kicked in. Time sharing kicked in. There they are. Come here, you. Reset that. That's irritating, isn't it? There we go. Cool. So, anyway, gosh. Thank you. But anyway, it sounds simple, but this was a very hard problem to solve, and it took us decades of kind of like putzing around trying to figure out how to make this happen. We would not be where we are without this. We would not have any of the things we have without cracking the virtual memory problem. And the first functional implementation of that was the Atlas supercomputer. I would argue that this is the single most important machine in computing history. But this was built as a joint venture between the University of Manchester and two companies called Ferranti and Plessy in 1962. This is it being booted for the first time, which is very cool. Ferranti did build two more of these systems, but they were never made commercially available. This was strictly an in-universities thing. There was also a derivative system called Atlas II, also called the Titan. It was built for Cambridge University, but it did not implement virtual memory, and I had to go back and forth a lot on different sources from both of those universities from decades ago to find out whether or not that was true, but the Atlas II did not indeed have virtual memory. Unfortunately, these computers are so old that there just isn't a ton of documentation about them, and we didn't decide they were important until a couple decades ago, and very few people left alive who personally remember operating them. But yeah, this is a very cool computer. They did not actually crack the problem, though, because these were not commercially available. It was unwieldy. It was not possible to make these commercially available. IBM was not going to be stopped, though. They were called IBM and the Seven Dwarves for a long time because there were other companies building mainframes, and they could not compete with IBM. And in the 60s, IBM began development of the System 360 series of mainframes. Maybe this might be the most famous mainframe machine in history. Unlike their previous product lines, the S360 series covered a range of speeds and price points. It wasn't just one machine. They were fairly modular. And they also were prioritizing backwards compatibility. At the time, if you bought a new mainframe machine, even if it was from the same manufacturer and it was a fairly incremental upgrade, you would also need to buy new printer, new punch card system, new everything. Absolutely nothing was interoperable with the previous generation of machines. And IBM decided they were not going to do that anymore. We're doing backwards compatibility. This was completely unheard of at the time. Not to be outdone by themselves, I guess, this is also the series in which they achieved full virtualization, including virtual memory, in a commercially available machine. Alongside the development of the machines themselves, IBM's Cambridge Scientific Center was developing the time-sharing operating system CP40 that would turn out to be the world's first ever virtual machine operating system. By 1967, and the release of the System 360-67, paired with the CP67 OS, we were fully in commercial use. This thing was widely available. Universities had it. And this ultimately won IBM absolutely complete dominance over the market. The trajectory of computing changed forever from there. None of what we have today would be possible without IBM gambling on virtualization and time sharing. The use of the word trajectory is intentional there because the IBM System 360-67 and the CP67 OS is what sent us to the moon. This was the first commercial implementation of a thing we would need to ultimately build Kubernetes. And it is the thing that sent us to the moon and handled the management of the Swedish rocket ship America ever built, the Saturn V, which is so cool. There's all of them. We don't have them anymore. They can't be used. But you can go see one in Huntsville, Alabama at the NASA Space Center. It's very cool. You should go see it. But from this point in history, with the virtualization problems cracked, things start moving fast. In '69, development of the Unix operating system began at Bell Labs. This version was intended for internal use at AT&T, and it remained that way for a while, but the Unix we have today is built on this original internal-only OS. And just 10 years later, in 1979, Unix 7 included the first step towards containerization that we know and love today, the chroot call, or change root, or however you want to pronounce that one. I don't know. Responses are mixed. If you don't know what this tool does, it isolates a program and its children by changing the program's apparent root directory, preventing it from being able to modify files outside of that directory in most circumstances. You can get around it, but this environment is called a chroot jail, and it's the first example of what we would eventually call a container. It's kind of a proto-container. This is where the virtualization timeline begins to diverge, though. The development of classic virtual machines advances and continues in another timeline through to today. We're still doing that, but we also have the path to containers. FreeBSD decided that they liked this idea. They thought this was good, this was going to go places, and they gambled again and decided to explicitly develop for this eventuality. They expanded support for chroot and introduced the jail command with its 2000 release. Unlike chroot, FreeBSD jails allowed for complete file system and root privilege isolation, CPU quotas, memory limits, that kind of stuff, a whole bunch of features that if you work with containers, you're very familiar with already. And at this point, everybody else kind of jumps on board. Virtuoso released one a year later, Solaris in 2004. vkernel and sysjail both released in 2006. There are honestly, there's so many of these tools that released in a 6 or 7 year span that there's no fixing them all on a slide. It was like a dozen different tools or more. These are just the most relevant ones. In 2008, the next jump towards modern container technologies saw the light of day, and that was the public release of C groups into the Linux kernel mainline. This was in development at Google from 2006, and it allows you to isolate and limit resource usage for a collection of processes. Many of the tools we rely on today directly rely on C groups, including Kubernetes. But it didn't happen immediately. It kind of stewed for a while. In 2008, we got LXC, which some of you may be familiar with, and in 2010, systemd nspawn. Both of those tools were also built on top of C groups, and we're probably firmly at the point in the timeline where I'm talking about tools that most of you have used. But nothing released so far solved the issue of portability and user-friendliness. Containers were useful, but they were not ubiquitous yet, and they were kind of fussy to work with. Microservices as a concept had not completely taken over modern software development yet. Just like mainframes and the move from batch processing to time sharing, it's not just the technical hurdle that matters. It's the accessibility, the ability to actually use and understand a thing. Docker kind of solved that. In 2013, it was released. We all know it. We all love it. Some of us also hate it. That's OK. I love it personally, but it built directly on lessons learned and the ideas of its predecessors, and it took off nearly immediately. If you go back and look at the Google Trends for Docker, it's nearly vertical. It was very, very, very rapid, and that I would largely attribute to its approachability, its ease of use, and its ease of sharing. Just 1 year after this, Google announced the first public release of Kubernetes with Docker as its first runtime. And that's how we got there. Decades of how do we do more with a single machine? How do we solve the problem of making a single machine act like many machines in an efficient, user-friendly, reliable way? Got us Kubernetes. Longer history than you would expect. So a whole industry has sprung up around this, around containers, with numerous startups, multiple foundations, reps from both of those in the room, and all of our careers, as well as more conferences than I personally know what to do with. This is my 8th conference in 2 months. So it's kind of eaten the world a little bit. We owe this entire ecosystem, which is increasingly stressful to look at, to 70+ years of iterating on the same problem. How do we do more of this, but faster? Looking back at the machine that first cracked the virtualization problem, the Atlas II, it seems primitive when you compare it to something like Kubernetes, and it was. But at the time, it was groundbreaking. There was no replacing it. It was a shot heard across the world, right? But we are still trying to scale bigger and faster with less effort. And I don't like the word scale because it doesn't mean anything. It's contextual. It only means something the moment you say it, and then 3 months from now, the definition of scale changes. But in this context, I think it is the right word. So what is going to make Kubernetes look primitive in 70 years? What is scale going to mean in 70 years? What is this landscape going to look like? Is the Linux Foundation still going to exist? And if it does, what is the CNCF landscape going to look like? I don't know. Thank you for listening to me.